Math 110, Permutations, Sections 8.5. Now the study of permutations involves order and arrangements. So let's look at an example to kind of demonstrate what that means. How many three-letter code symbols can be formed with the letters A, B, and C without repetition? That is, only using each letter once. So maybe a way to imagine or envision this is, what if I took these letters and I placed them in boxes? The idea is, how can I take these boxes and rearrange them? Meaning, could I take the A and put it in front here? Could I take this B and I could put it over there? And so the idea is all the different possible arrangements of those three letters. That's what it's asking. Now what's going to help us is creating a tree diagram to examine or at least take a look at those outcomes. And so if I start with the letter A, then I'm left with two more possibilities. It could either be B or C. If I choose B, I'm forced to choose A. If I choose C, then I'm forced to choose B. Then if I start with B, my other two options are going to be A or C. If I choose A, I have to choose C. If I choose C, I have to choose A. And so on and so forth until you get all the combinations. And so all of my outcomes would be these values here. And so how many three-letter codes could I make? It would be 6. And so the set of all these permutations is going to be the outcomes. Now, the fundamental counting principle says that given a combined action or event in which the first action can be performed in n sub 1 ways, the second action can be performed in n sub 2 ways, and so on. So the total number of ways in which the combined action can be performed is the product. And so you're taking these combinations, or at least these whatever the event is, and you're going to be multiplying them together. And so if we're performing like an experiment, such as selecting these letters like in the previous example, or flipping a coin, or even drawing a card, that result is going to be called an outcome. And then an event is going to be the set of all of those possible outcomes. And so looking at this example, how many three-letter code symbols can be performed with the letters A, B, C, D, and E with repetition, that is, allowing letters to be repeated. And so using this previous definition here, we have to think about it, that first choice, how many possibilities, times my second choice, how many possibilities, times my third choice, how many possibilities, etc., etc., etc. And so looking at it this way, if I'm saying how many three-letter code symbols can be performed with these 5 different letters, and I can repeat, well, my first one is going to be 5. Well, since I'm able to repeat, my second one is also going to be 5. And since I can repeat, my third can be repeated, etc. So I'm just going to get 5 times 5 times 5. And then you multiply those together, and you get 125. Now, what if there are no new repetitions? Meaning I'm not allowed to repeat. Well, then my first selection, I'm going to have 5. Then my second selection, since I'm not allowed to repeat, it's going to be then 4. And then my third selection, because I'm not able to repeat the first 2, I'm only going to have 3 left. And then if you multiply those together, you're going to get 60. Now, a permutation of a set of n objects is an ordered arrangement of all those n objects. So imagine the set of these 4 objects, A, B, C, or D. A permutation is taking those 4 objects and rearranging them without repeating. Now, the total number of these permutations of these n objects is defined by this definition here, npn. And so n times n minus 1 times n minus 2, all the way down until you get 1. So let's find each of the following. Let's kind of practice that. So 4p4, this is the number that we start with. This is how many factors I'm going to be having counting down. So if I have 4p4, the number that I start with is going to be 4, which is what I have here. And then this 4 is the number of factors I'm going to be having counting down. So 4, 3, 2, and 1. There's 4 of them because that number is 4. And so if you multiply these all together, you're going to get 24. 7p7, you're going to start with the number 7. And then this 7 is the number of factors counting down 1, 2, 3, 4, 5, 6, 7. So 7 times 6 times 5 times 4, etc. Multiply those together, and you're going to get 5,040. Example number 4, it says, in how many ways can 9 packages be placed in 9 mailboxes? 1 package in a box. That's just 9p9. I have 9 packages, and I'm trying to place them in those 9 boxes, 1 per box. So this is going to be the number of the number that it starts with, and these are going to be the number of factors, 1, 2, 3, 4, 5, 6, 7, 8, 9, counting all the way down. And so multiplying those together, you get 362,880. Now, instead of writing this long statement, 7 times 6 times 5 times 4 times 3 times 2 times 1, it's a little annoying. And to be completely honest, it can get really tedious when you're doing that. And so we create this type of notation called factorial notation to help us. And so instead of writing it as 7 times 6 times 5 times 4 times 3 times 2 times 1, we're going to write it as 7 factorial, and it's actually read as 7 factorial, and that's what that exclamation point means. So our factorial notation, by definition, is going to be n factorial equals n times n minus 1 times n minus 2, and you're going to count all the way down till you get 1. And just for the purpose of allowing all these definitions to work in the future, we're going to let 0 factorial equal 1. And if we don't do that, weird things happen. So example number 5, it says rewrite 7 factorial with a factorial of 5. So normally, this is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, I want to write it with the 5 factorial, so I want to keep this portion here. Okay, so I want to keep that portion there. And so I could rewrite that portion as 5 factorial. And so I just replace it with 5 factorial, and it answers the question. Now, permutation of a set of n objects taking k at a time is an ordered arrangement of k objects taken from the set. And so we're going to use the formula. The number of permutations of a set of n objects taking k at a time is denoted npk, is going to be given by this formula here. npk equals n factorial over n minus k factorial. So compute 8p4 using both of those forms. We're going to try that previous one in the very first, and then we're going to try using the definition. So using that first one, starts with 8. This is how many factors that I have, 1, 2, 3, and 4. So I don't have the 4 times 3 times 2 times 1 because it says you only have to have 4 counting down. So 8, 7, 6, and 5. And so computing that, you'd get your result, 8p4, using your notation here. 8 is our n, 4 is our k. And so you get 8 factorial over 8 minus 4 factorial. Now you can't just reduce this and say, oh, well, the 8 and the 4 reduced into 2. It doesn't work that way. You actually have to write this out, or you have to use your calculator to represent that. And so writing that out, you're going to see that the 4, 3, 2, and the 1 are going to cancel out. And so 8 times 7 times 6 times 5, that's going to be 1,680. Example number 7, it says the flags of many nations consist of 3 horizontal stripes. For example, the flag of the Netherlands has its first stripe red, its second white, and its third blue. Suppose that the following 7 colors are available: black, yellow, red, white, blue, orange, and green. How many different flags of 3 horizontal stripes can be made without repetition of colors and a flag? So it's saying we have 7, and I'm choosing 3 colors. So that's going to be 7 different colors taken at 3 at a time, and there's not going to be any repetitions. So that's just 7p3, which is 7 factorial over 7 minus 3 factorial. And so that's just going to be 7 times 6 times 5, which is going to be 210. A baseball manager arranges the batting order as follows. The 4 infielders will bat first, Then the 3 outfielders, the catcher, and the pitcher will follow, not necessarily in that order. How many different batting orders are possible? So it's talking about 2 different things. We have the 4 infielders, then we have the 3 outfielders, the catcher, and the pitcher, and those are grouped together. So our counting principle is we're going to have to take both of those values and eventually multiply them together. So first, talking about the infielders, that's just represented in 4p4 ways. And the 3 outfielders, the 1 catcher, and the 1 pitcher grouped together, that's going to be represented as 5p5 different ways. So you just multiply those together, 4 factorial times 5 factorial, and that's going to give me 2,880 possible batting orders. Example 9, how many 5-letter code symbols can be formed with the letter A, B, C, and D? And so we can select each of the 5 letters in 4 different ways. So I want to create 5-letter code, so it's going to have 1, 2, 3, 4, 5, but didn't have any restrictions on it being repeated. So my first letter, I can select it 4 times. My second letter, I can select it 4 times. My third letter, I can select it 4 times. My fourth letter, I can select it 4 times. My fifth letter, I can select it 4 times. And so that's going to give me 4 to the 5th power, and that's going to be my answer. So the number of distinct arrangements of n objects taking k at a time, allowing the repetition, is n to the k. Now, consider the set of 7 marbles, if we have 4 being blue and 3 red. When you actually line them up, the red marbles look like any other red marble. And so in this instance, we're going to say that those red marbles are going to be non-distinguishable. Meaning, like, if I take those 2 marbles and I were to switch them, nothing changes. And so for a set of n objects, which n sub 1 of one kind and n sub 2 are another kind and n sub k are of the kth kind, the number of distinguishable permutations is n factorial divided by n sub 1 factorial, n sub 2 factorial, ... all the way to n sub k factorial. This is representing those 4 blue marbles and those 3 red marbles. And so looking at an example of that, in how many distinguishable ways can the letters of the word Cincinnati be arranged? Well, I have 2 C's, I have 3 I's, I have 3 N's, I have 1 A, and I have 1 T, but I have a total of 10 different letters. So I can select it 10 factorial times, that's how many times I can rearrange it. This is 10p10, but I have to get rid of those repeats. And so getting rid of those repeats of just those C's switching or the I's switching or the N switching, so that's going to be 2 factorial times 3 factorial times 3 factorial times 1 factorial times 1 factorial. And so that's going to give me 50,400.